And then in the next lesson, we'll learn about what this looks like in practice. Does that make sense? So this is lesson 3.8, reaction kinetics. All right, so yesterday was about just calculating the rate of reaction from an experiment. But today's not going to be about an experiment. It's going to be about what's actually happening at the atomic level. In other words, why do some reactions happen quickly and other reactions happen slowly? So team, why do some reactions happen quickly and others happen slowly? Okay, very good. So one would just be the chemical properties, the reactivity of the materials involved, the species involved, whether they be elements or whether they be compounds. Absolutely. Electronegativity, polarity, yeah. Okay, absolutely. So for example, when we heat up an environment, what does that do to all of the actual chemical species? What is the effect? What does it mean to heat something up? They're moving faster, right? And in fact, that's going to be a big piece because if things are going to react, what do they have to do? They got to bump into each other, right? So that's what we're going to talk about today, which is that like reactions occur. Absolutely. So reactions can only occur when compounds, elements, and we're going to put the term here, different species. That's a term we use in chemistry. The species involved in the reaction collide with one another. All right, an example, we could have something A plus 2 B's has to result in the formation of AB2. Does that make sense? We're just doing an imaginary kind of reaction here. Does that make sense? For this to happen, you have to have something A, and it has to bump into 2 things B to give us this AB2. Okay, whatever that might be. So, with that in mind, what might actually happen there, bless you, is this can happen all at once or in stages. So when we have a reaction happening, that actual reaction can happen all at once. So it might be that for this reaction to happen, an A and 2 B's have to bump into each other all at the exact same time. Does that make sense? That's a possibility. But the other possibility is that it happens in stages. Does that make sense? And if we use the same example, e.g., A plus 2B yields AB2, could take 2 steps. It could be that A plus B yields AB, and that AB bumps into another B and gives us AB2. Does that make sense? Yeah. Yep, I'd be happy to. So a lot of reactions actually take more than one step. Does that make sense? A lot of reactions actually take more than one step. So if we keep that in mind, in this case, that would look like an A bumping into a B to form AB. And then the second half, it would look like an AB bumping into a B to form AB2. We would still write the reaction for all, we still write this as A plus 2B yields AB2 overall. Does that make sense? In other words, when we write a chemical equation, we're typically writing the overall equation. The best example of this is, remember in grade 9 we teach you photosynthesis, is the reaction 6 CO2 plus 6 water plus sunlight gives you sugar and 6 oxygen. And then if you take grade 12 biology, you learn, ha ha ha, joke's on you, that's actually like 50 reactions, right? That go step by step by step by step. Do you remember that? Who took grade 12 bio already? Lot to learn there, right? That photosynthesis reaction doesn't happen in one step. It doesn't even happen in 2 steps. A glycolysis itself is 10 steps. And then you get pyruvate oxidation and moving into the mitochondria and all this thing, right? Like cellular respiration, where glucose gets burned into carbon dioxide and water, takes, 30 steps that happen in like 5 different places. Does that feel okay? The idea that just because we write a reaction doesn't mean that reaction has to happen in one step. You could think of it this way. If you look at a Lego set, you could say the reaction is you take all these Lego pieces, you put them together, you get the Death Star, right? And that's true. That is a true statement. You need 50 of these pieces, 2 of those pieces, write out all the pieces you need, you put those all together, you get the Death Star. But if you're actually going to build it, you've seen those manuals before, right? First you put these pieces together, then you put those pieces together, then you put these ones together, now you take this big piece, attach it to that big piece, and it goes step by step. Does that make sense? Okay. This is an important concept when considering the speed of a reaction. Sometimes we do, but keep in mind we don't always know the steps, right? It's easy as a scientist, relatively easy, to find the overall reaction that's happening, right? You start with the stuff you start with and you see what you end up with. Now ask yourself, how do you find out what the middle steps are if this is happening quickly on a really small scale? Not so easy, right? So it's actually very sophisticated work to figure out what the intermediate steps of a reaction are. And we know how to do that for some reactions, but we by no means know how to do that for every reaction. That was a great question, by the way. And you're going to see that it factors into one of the ways we actually figure intermediate steps out is by how fast a reaction happens. And we'll talk about that in a minute. So this is an important concept to remember when considering the speed of reactions. Okay. Shh, quiet. Thank you. Okay. So now we're going to go rate laws for reactions. For any single-step reaction, A plus B yields C. Okay. If 2 things have to bump into each other, what will the rate depend on? Well, the rate of that reaction is going to depend on some constant K, and then that is going to, it's going to depend on temperature, pressure, yep. Type of reactants, etc. But if none of that stuff changes, that'll all be constant, okay? So there's going to be some constant value, but as a reaction happens, what does change is how much stuff you have, right? And remember, for this reaction to happen, A has to bump into B. So if I want to make that more likely, what could I do? Now, we know we could increase the temperature, but we're going to say the temperature is constant, right? We're setting this at a constant temperature, constant pressure, all that. But if I want there to be more A bumping into B going on, what could I do? I could add a bunch more A. If I add more A, that's going to happen more often. And if I also add more B, it's going to happen even more often. Does that make sense? So that's a linear relationship. If you double the amount of A, then B should bump into A twice as often. And if you triple the amount of A, then B should bump into A 3 times as often, right? And if you have 10 times as much A, B should bump into A 10 times as often. Does that make sense? So it's linear, which means that we can just multiply this by the concentration of A. And then we can, the other thing we'd say is, if I then also double the concentration of B, well, now the reaction should happen twice as often. And if I triple the concentration of B, it should happen 3 times as often. In other words, it's linear with respect to concentration. So we could say that. Does that make sense? This is a linear relationship. Okay, but now let's consider a one-step relationship, a one-step reaction, A plus 2B yields C. Doesn't matter what C is. In this case, an A doesn't have to bump into a single B. It has to bump into 2 of them. Okay, now think about that for a minute. Because now, if I'm an A, all right, and I'm looking for a B, I don't have to bump into one of them. I have to bump into 2 of them. So now, that's going to be harder to do, right? But on the other hand, if I double the concentration of B, then I'm going to be twice as likely to bump into this B, but I'm also going to be twice as likely to bump into that B. Which means if I double the concentration of B, the reaction shouldn't happen twice as fast. It should actually happen 4 times as fast. Think about that for a minute. It makes sense because I have to find both of these. So if this is twice as likely to happen and that's twice as likely to happen now, then overall the reaction is 4 times as likely to happen. Does that make sense? So in this case, the rate would depend on, again, some constant K, which is going to be dependent on the temperature, the pressure, the type of the reactants, etc., times the concentration of A, because doubling the concentration of A would make this thing twice as common. But when I double the concentration of B, I actually have to factor in the concentration of B twice. Because one sec, but we'll get to you. Because we have to bump into B, but then we have to bump into B again. Which means that altogether, the rate would be equal to some constant K times concentration of A times concentration of B to what exponent? 2. Does that make sense? So, what this tells us then is, in general, for any one-step reaction, not plus, whoops. What doesn't it depend on? What have we not looked at in any case? It doesn't depend on the concentration of the product, because the product doesn't actually have anything to do with the reaction, right? It's not the product that matters. The reactants have to bump into each other. Yeah?
Why
we're saying that it's all happening at once. One step means it's not happening in stages.
Okay.
It's happening all in one step. Does that make sense?
Yeah,
So up above, this we said wasn't a one-step reaction. This was a two-step reaction. For A plus 2B to give us AB2, we said in this case, it doesn't actually happen all at once. A has to bump into B first. That happens. Then AB bumps into B, and now we get the AB2. It happens in two steps. Here, we're saying what happens for one-step equations, single steps. All happens at once.
Okay, I was just because we called it single step and then
Yep,
one
all
step.
happens at once.
Didn't A matter?
Yep.
How would we know that it is a one-step reaction?
Well, the way you would know is that you would test it, right? In theory, if this is true, so for this one here, then you would just do a test. And you'd say, okay, if I start the reaction and I measure how fast it goes, great. Now if I double A and the rate of the reaction doubles, I'd say, okay, that makes sense, check. And then if I double the concentration of B, I start again, I double the concentration of B, but now the reaction doesn't go twice as fast, it goes 4 times as fast, then that means that this mathematical equation that we'd expect would be true, and then I'd say, oh, that must be a one-step equation. It's got to be happening all at once, because clearly A has to bump into 2 B's for this to work, because if I double the concentration of A, it goes twice as fast, which means A is bumping into something. But then when I double the concentration of B, it doesn't go twice as fast, it goes 4 times as fast, which means that bumping into B is happening twice. Does that make sense? No, so that would be a one-step. We're saying that is all happening at once. The fact that 2 B's have to collide to make this happen means that the collision with 2 B's is happening in that single step, not being broken into separate steps. Has to happen all at once. Sit on it for a minute. Maybe by the time we get to the end of the note, it'll make sense. Same thing. I don't even know what you're asking, but sit on it for a bit. Just stop interrupting. It's not going to help the flow, I promise. Okay? Just trust me. All right. So when we do a reaction, generally speaking, if it happens all at once, if it all occurs at once, then this is the relationship. For example, let's do a simple one. For example, a really easy one. Sorry, I'm blanking here. Carbon plus oxygen yields carbon dioxide. Does that make sense? That's our balanced chemical equation. Is a one-step reaction. And so then we could say, write a rate law. So this is a nice simple one. We want you to write a rate law equation for this single step reaction. All right? So we know what we're doing with that, but now we're dealing with a real equation. And I'm going to let you, for this one, we can talk about the concentration of carbon. I know that's kind of a weird thing to describe here. Just work with it. Just write concentration. We'll get to why we cheat and just discuss concentration later on. For now, I'm going to say, trust me. So write that. What would it be? Rate would equal, and we're not going to try to know the value of the constant K yet. The way you would do that is just experimentally. You'd run the experiment and you would get the value of K. And spoiler alert, that's what we're doing tomorrow. So now I'm just going to ask you to accept that there will be some value K. Does that make sense? And again, that depends on a lot of things. Temperature, pressure, the nature of the reaction, electronegativities, all the things you guys mentioned. We'll do a day on that. The size of the volume involved, like all these things. Yeah?
That whole rate thing, C is not the product, right? C
No, the product here is...
Yeah, I know, but like for the thing above that, where it says rate K, A, B, C.
Yep.
Is that the product?
In this case, D is the product.
D is the product.
Yeah. So we're never looking at the products because the reaction doesn't actually depend on the products, right? Like if you're working in a factory, you don't need the finished cars to make new cars. They're off going to the lot. what you need are steering wheels and windshields. And you can tell I'm not somebody who's ever worked in a factory because I'm describing like what a little kid thinks is how you put a car together. When the real answer is like this bolt and like this tie rod control arm. But I'm like, well, you're going to need wheels and I need a steering wheel and there's like a windshield, you know, like I've like a little kid understanding of how one builds a car. Yeah.
So basically, would you tell basically where the like round is? Because it's O2, but if it's 2O, does that?
Yeah, O2 is a single thing, so there isn't a number in front. So if you look here, it's only the coefficient. It's only the number in front that becomes the exponent. So in this case, is there a number in front? No. So what will the rate equation be? Some constant, which we call k, right? So I've been told that my lowercase k's look like, I'm just worried that they look like, I'm sorry, I don't know what to tell you, they're kind of semi-cursive. So k, okay, how's that one? That's okay? All
I
right.
thought it was R.
I'm sorry. I'm sorry, and then what would it be times? Concentration of C? And not plus. Not plus. Multiply. We're working with probabilities here. That's really what this is about. It's the probability of this happening. Speed is just a function of how likely these things are to bump into each other. Does that make sense? And we rarely add probabilities, we multiply them, right? So K times concentration of C times concentration of O2. And that's it. And in this case, they'd both be 1s because that's just, there is no exponent there, right? Does that make sense? Let's try another example.
Do you not put like an arrow to make it C, like put CO2 at the end? Wouldn't it be O squared?
No, O2 is a single molecule, right? O2 is not two O's. Those aren't the same thing. I know we think that way, but remember, O2 is a single molecule. Because if you try to move one of those atoms, they both move, right? So you always get them both at the same time, right?
Why is it squared in the previous example?
Because in the previous example, it was a coefficient. Did that answer your question? It's a good question. So let's try another example. Let's say that we have, yeah,
Why are we not like, you know how the product is CO2? Why are we not putting the product in like the rate?
because it has nothing to do with the rate.
Oh.
The product, and again, if you think about that, makes sense. Once it's become CO2, it floats off and does its own thing. It has nothing to do with the reaction carrying on. Does that make sense? Because the CO2 doesn't have to do anything. It's gone. It's been made. It's the carbon has to bump into the oxygen. Oh, I put Ag. I did not want to put Ag. Sorry about that. I wanted to put Mg. And it's 2 plus. Sorry about that. This is an ionic equation. And let's say that we are forming magnesium chloride. Okay. Again, this is a one-step equation. If it's a one-step equation, this one, we're assuming it is for the moment. So if it's a one-step equation, then what does the rate depend on? Rate would depend on, take a minute and write it down. Yep. Sorry? Yeah, if you double CL, because you have to bump into them, bumping into the first CL is twice as likely, and bumping into the second CL is twice as likely, so overall it becomes 4 times more likely. So how would I write this equation? You want to give it a shot? Yeah, very good. By the way, it's really important that this be a lowercase k, because we're going to use uppercase k's later. So just, that's important. And my uppercase and lowercase k's always seem to look the same. Anyway, carry on. Concentration of Mg, 2 plus, right? Yeah. And does that get an exponent? No, because its coefficient is 1, right? Good. And? Cl minus, yep. And that's going to be squared. Good. You should. They're different things, right? It's not like you're not understanding the concept if you don't, but it's kind of bad manners. They should be there. How's that feel? Does that feel okay? So that's actually really easy. Here's where it gets ugly. I want you to imagine, all right? We're going to step away from this for a minute. Let's say let's say that our we're going to do multi-step rate laws. Okay, and we're going to start with an analogy. All right, ready? And here's my analogy. Ready? It is flour plus water plus yeast plus bacon can yield a bacon sandwich. All right. Now, as you know, this is not a single-step reaction. I don't care how hard you try. I don't care how hard you try. You cannot throw flour, water, yeast, and bacon into a bowl, shake it, and get a bacon sandwich out of it. It's just never going to happen, right? And we all intuitively know that, right? So, what has to happen? Well, instead, it would look like this. It would be flour plus water plus yeast can give us bread, right? Bread can become slices of bread, right? Bacon raw can become bacon cooked, right? That's an important step. And then we can say slice of bread plus bacon cooked can give us our bacon sandwich. Does that make sense? How's that feel? Now, let's go in analogy time. How long does this take? Or you could say, in other words, how fast can you do that, right? You don't have to change it. How long works just as well, but how fast can you do that? Well, how fast could you make flour, water, and yeast into bread? Anyone bake bread here? You have to let it rise. Nothing about it, right? No matter what you do, you got to make it rise. And that has to sit for a few hours. So like the fastest I think you could do this would be about 6 hours. It has to proof, it has to bake, it has to cool before you're going to slice it. Yeah? Okay, cool. If I have a proofer, how fast could I do that? I'm going to be speedy. And then the actual baking, so maybe, and preparing it, so maybe an hour all in. Okay, we'll say 1 hour. Okay, that'd be the fastest we can do that. What about taking bread and slicing it? Yeah, if even, right? I'm going to say 1 minute, right? Then I'm going to say this doesn't have to happen after that. This can happen all on its own, right? Does that make sense? So raw bacon into cooked bacon. Hey, how long does that take? Probably 15 minutes, right? I mean, if you go faster than that, it gets really wavy, it gets crummy, right? If you want to have nicely cooked bacon, you're looking at least 15 minutes. Is that fair? Okay. And then putting together the slices of bread, and the cooked bacon to make a sandwich, you can do that in a minute, right? Okay, now, it's so good to see you. If you have all these things where you can be doing all these things continuously, right? What's the thing that's going to slow you down the most here? Yeah, no matter what, you could, like these two have to happen together, I guess, but the slicing the bread, certainly could be done while the bacon is being cooked. You could even do it during the construction of the sandwich, right? You know what I mean? In the end, the thing that's going to slow you down, the fastest you could possibly do this would basically be 1 hour and 2 minutes, And if you have this constantly going on, the thing that's always going to be slowing you down is the thing that takes an hour. Does that make sense? In the end, in this example, the bread baking step determines the speed at which you can do it because it's the slowest. So we would say that if you could be doing all of these over and over and over again, such that you have some bread stockpiled, you have some bacon stockpiled, you can be making sandwiches all the time. Once you get to the point where you have stockpiles, the only thing that would help you speeding up would be speeding up the bread baking process. Does that make sense? If you've got all these things on the go and you learn how to slice bread twice as fast, it's actually not going to speed you up one bit because slicing the bread wasn't slowing you down. If you learn how to cook the bacon in 6 minutes instead of 15, it's actually not going to speed you up at all because you're still going to be waiting on the bread. And if you learn to put sandwiches together 8 times as fast, so you can do it in a second, you've gotten so efficient, it's actually not going to make any difference because you'll always be waiting for the bread. Does that make sense? In the end, the slowest step determines how fast you can go. The slowest step determines how fast you can go. The way we do relay races, it's like you run a quarter, then you hand it off, and then you run a quarter, then you hand it off, then you run a hander, then you quarter it off, right? But if you did a relay race instead, where it was just like your whole team had to run and just you don't get to go to the next quarter until everyone gets there, then the person who would determine how fast you can run is your slowest runner. Does that make sense? You'd always be waiting for them. And I feel like that would be me, and then people would be mad at me, and then I'd be self-conscious. But enough about my anxieties. Does that feel logical to you? Yeah.
So in like a normal reaction, how would you know which one's the slowest?
That's a great question. And the answer is you'd have to do experiments, which is what we're going to look at tomorrow. Because again, you don't even know what the steps are necessarily. So now let's look at a multi-step reaction. And in this one, we're going to say 2A plus 2B yields something C. Okay? Is the overall. But actually, this happens in 3 steps. Step 1 would be A plus A gives us A2. That's our first step, okay? Does that make sense? So you can imagine that for the first thing that actually has to happen in this reaction is the 2 A's have to bump into each other. Does that make sense? Then in the second reaction, our new A2 is going to bump into a B, and it's going to give us A2B. All right? Cool. And then in the third reaction, we're going to get A2B bumps into B again, and it's going to give us A2B2. All right? This is a made-up reaction. All right? Made-up reaction. Put your hand down. Just put your hand down. All right? Does that make sense? How this reaction, and that is what we call C, by the way. All right? This thing here, A2B2, is just C. All right? That's the end of our reaction there. Okay? In fact, if you want to go up and just change this to A2B2 at the beginning, just to make our life easy. Okay, there we go. That's our reaction. Now, the question is, what would be the rate for each of these? Well, the rate of this one would be some constant K times what? concentration of A, and actually concentration of A, and then again times the concentration of A, which we could write like that, but what's a better way to write it? A squared. Okay, that first step depends on that. Now what about the second one? What would the rate of this one be? Of A2, right? That thing we just made. Yeah, times concentration of B. Okay, very good. And then this third one? Times the concentration of B. Okay, now, in this case, these are things that don't really exist, sort of except around us. But here, now, what if we discovered that this reaction happens really fast? And this reaction happens really fast. But this reaction here is slow. Does that make sense? If step 1 is the slow step, it will determine the overall speed of the reaction. Which means for the reaction 2A plus 2B gives us A2B2. The rate may end up being, in this case, the rate is some value K times A squared. This reaction, as you add B, it may make no difference. And that answers your question. Well, how would you know? Well, the answer is, when you go to do the reaction, if doubling how much B you have doesn't make the reaction speed up at all, then you know that reaction must be in steps, and there must be a step that doesn't involve B. Does that make sense? On the other hand, if you did a reaction and adding A doubled it and B doubled it, then you'd know there's some point where A is colliding with B, and that's the slowest step. So we can determine what the slowest step of a reaction is by doing experiments and seeing how things change. You either have to know the steps of the reaction. You must know the steps of the reaction. And which is the fastest, or which is the slowest, rather, to do this theoretically. Otherwise, we have to do experiments to determine the slowest step. Yeah.
So if you go up to the overall reaction,
Yep.
like you write the rate as concentration A squared, concentration B squared.
If it were a one-step reaction. If it were a one-step reaction. But we're told right here that this is a multi-step reaction. And again, you can test that, because if this is a one-step equation, then doubling A will make it go 4 times as fast, and doubling B will make it go 4 times as fast. And if that worked, then you'd say, oh, this is a one-step equation, because the predicted rate law, because that's actually worth putting here. The one-step rate law would be, you're right, rate equals K times concentration of A squared times the concentration of B squared. So if you experimented and that worked, yep, doubling A makes it go 4 times as fast, tripling A makes it go 9 times as fast, making A 10 times bigger makes it go 100 times as fast, oh, doubling B makes it go 4 times as fast, tripling B makes it go 9 times as fast. If that all worked, then you'd say, oh, this is a one-step equation. This all happens at once. But in this case, we're being told it doesn't. In fact, in this case, you can add B till the cows come home and it doesn't speed up at all, which means any step that involves B is a fast step. It happens quickly. It's like cutting the bread. It doesn't matter. And in fact, only changing A matters, but doubling A doesn't just double the speed. Doubling A actually makes it go 4 times faster. That tells you there must be a step where A is bumping into A, right? The fact that those two things must actually collide with each other for this reaction to happen, because it's a square relationship. There must be a step where there's 2 A's involved, and that's the slow step. And because B didn't change anything, that step must just be those 2 A's colliding. Does that answer your question? This is sophisticated stuff. It's challenging, yeah.
If you did B plus B as the second step, instead of A2 plus B and then did A2 plus B2, would that make both 1 and 2 the slow steps? And it would be overall slow?
The only way to know whether it's slow or fast is to do experiments. Does that make sense? You have to figure that out. No different than, unless you knew that baking bread takes longer than slicing bread, there's nothing to do with the fact that one involves 2 of them or this or that. This information here, you would have to get experimentally.
Yeah.
Did that answer your question? You can't predict. You're not going to be able to predict what the slow step is. You have to be, either the question might tell you, or you have to figure that out by doing experiments.
But if I did that,
Yeah.
if I did A plus A, then B plus B,
Yeah.
both of those would be the slow step.
Not necessarily. No, not necessarily. Again, it just depends. It might be that B bumping into B and turning into 2B or into B2, that happens really quickly. That's easy. Every time they bump into each other, it happens. It just is. Like in other words, here's the deal. Like if you're the guy who like, why is it fast to slice bread but it takes a long time to bake bread? We get right into the weeds. Well, when you bake bread, you have to knead, it has to proof. But a simpler answer is just, if you're going to slice bread, you go, and it happens. Baking bread takes longer. You have to wait for it. Likewise, it might be that A sticking to A just happens quick. Every time they bump into each other, it just happens. Whereas maybe with B bumping into B, maybe that's really direction dependent. Maybe that they have to be lined up just so for it to happen. Or maybe they have to hit each other going faster than A and A do. There could be all kinds of reasons why together. In other words, if you had 2 things that had Velcro on them, getting them to stick together is going to be easier than getting 2 things to stick together that don't, and maybe you have to tie them together. Like, there's just the properties of the chemicals involved is going to determine what's a fast step and what's a slow step.
Is there a way to determine that?
Not easily. The easiest way to determine it is just to do an experiment and see. By all means, if you had a richer knowledge of organic chemistry and physical chemistry than I do, you would definitely be able to make some predictions. I would say, for example, a single element, like an atom bumping into an atom and combining, is almost always going to be a more sure thing than 2 big bulky things that probably have to bump into each other with really specific shapes. If the step requires 2 things that are both charged to bump into each other, that's going to be slow for sure, because they'll tend to repel each other. Whereas if they have opposite charges, that'll be much more likely because they're fast. So there's definitely things that could give you hints, but in the end, to be sure, you'd have to do an experiment. Did that answer your question?
A little bit.
Cool. That was a really good question, by the way. It was a good one. Yes.
Will reactions always happen faster when it's warmer because they're like moving faster? Or do some
I don't want to give a global yes, because I'm sure there's some weirdo example I'm not thinking of where actually moving slowly is an advantage. But like in the overwhelming majority of cases, higher temperatures are going to mean things are moving faster, which means they collide with more force, which means reactions happen. The one other caveat I could give is it might mess you up in the sense that sometimes if the temperature gets high enough, all of a sudden now a different reaction is favored. And so even though your reaction in theory would speed up, you might get this other reaction instead. For example, when we did our esters lab, we wanted to heat it up, but I said stop at between 75 and 80, because if you got up to 85, all of a sudden now you're going to get something else happening altogether, which is your alcohol is going to boil off. So that would be another caveat, which is like when you get to a certain heat, now instead of the reaction you want, something else might happen. It might explode, right? That would be bad. So in general, hotter means faster reaction, but that doesn't always mean hotter is better because there's other things to think about, which is also a sophisticated thing. That was a good question. Did I answer it at all? That makes sense? Okay. Yes.
What is the difference between a single step reaction and a 1-step reaction?
There is no difference.
Okay.
You're really hung up on this.
Yes.
Would you like me to go back and change it so it's all? No, I'm not changing it so it's all the same. You'll hear both terms. Yeah, single and one are synonymous. Yeah, so they mean the same thing. Is that what your hand up was about
Yes.
before? I felt like I already answered that. But okay, we good now?
Yes.
We got it? Okay, good. Anything else? This is weird stuff, right? But the big thing I want you to take away is this, twofold. One, if everything had to happen at once, it would be really easy to do this. You just look at the equation and you just multiply the concentrations of each species to the exponent of the coefficients. But it's not that easy because in real life, reactions often don't happen all at once. They happen in steps. And because they happen in steps, in fact, you could have a reaction where the rate law doesn't line up with the equation because it's only lining up with the equation of one step of that reaction. Does that feel okay? That's a sophisticated concept. Yes?
So, like, if you wanted to see if it's a one-step or a multiple-step reaction, would you have to, like, break it down as
Yeah.
much as possible?
There's different ways to do it, but tomorrow I'm going to teach you the conventional way which we figure this out in lab. No, tomorrow we're going to do it on paper. And then this is one of those labs that I usually do, but boy, we are 6 days behind. So are we going to do it? I don't know. I don't know, T. Maybe, maybe not. We'll see. I don't know. I got to figure out what I'm cutting out. Huh? We are 6 days behind. Because they just keep scheduling stuff to be during the school day. So like, hey, university fair. Hey, college fair. Hey, volleyball tournament. Hey, basketball tournament. Hey, and they're killing me, man. They're killing me. And then I was gone for 2 days. One of those is what I would have done anyway. But yeah, we were 5 days behind before. Now we're 6. So yeah, we're dying. We're dying, yeah.
So how come it's just a square, not a circle?
Great question. So again, because it depends on the slowest step, right? So if we went back to this example, the rate depends on how much flour, how much water, how much yeast you have, because that's going to speed your bread making process up. But you could add bacon all day and it's not going to make you make your bacon sandwiches any quicker, because in the end, what's slowing you down is making the bread. Likewise here, in this reaction, even though the overall reaction has 2 A's and 2 B's, the slow step, the step that's slowing you down in this case, is when A bumps into A and turns into A2, that reaction's the hard one. That one doesn't always happen. That's the one that slows you down.
So when you know the slowest step, what?
Knowing the slowest step of a reaction will tell you what the overall rate law is. Very good. Yep. So I have a question for you. And this is going to be your homework question. It's just one. This one will not take you long.
Grade 12, if you have not booked a grad appointment, they are next week. We need you to do that today. Could you please come to guidance during lunch and book that appointment? Thank you. That's grade 12 to guidance to book a grad appointment.
Shh, quiet.
So, like, do you have tomorrow's lesson for jams?
Nope, sorry. That could still be possible, by the way. It's just not what I wanted to do here. But we'll talk about that. Like steps can also involve unmaking things. I'm trying to keep it simple for now just to not do that. But to be clear, okay, now. Yeah. There'll always be a slowest step, right? Like you would actually get these out with numbers, but in the end, statistically speaking, you're not going to have something that takes the exact same amount of time as another reaction. There will be a slowest step. Yeah.
For like the reaction above when we did like A plus A and A2 plus B,
Yeah.
would we not have done like A plus A and then A plus B and then A2 plus B?
We could have. I'm providing you with what the steps were. So the thing is, like when you get into organic chemistry, boy, the intermediate steps of a reaction, sometimes there's like 35, right? Like it's really complex. And it's not, well, couldn't we do this 15 other ways? Sure, in theory, but in practice, this is actually what happens. Like these are actually the steps that get followed. Does that make sense? Like, you could put your shoes on, then cut holes in the soles of your shoes, pull your socks up through them, and then put the soles back on and glue them back together. That would work, but in practice, that's not what happens, right? Like you put your socks on, then you put your shoes on, right? And maybe you put your left sock on, then your left shoe on, then your right sock on, then your right shoe on, but probably you don't. Probably you put both your socks on, and then both. Do you know what I mean? Like, just because something could potentially work that way, what we're talking about here is what actually happens in nature. The action. Did that answer your question? That was a good question. I felt like that was a crummy answer. Yeah. Let's go with you first, then. Ken.
Do we have a self-taught lesson this unit?
Eventually, yes. Yet, no.
What?
Eventually, you will, but I haven't given it to you yet.
I love like so.
I know, isn't that adorable? It's really cute. How you doing? I'm doing well, so you're getting down to it.
Yeah.
Are we surviving? Are we thriving?